Hey everyone, and welcome back for another deep dive. This
Okay.
time, we're going to be looking at feedback control systems.
Oh, yeah.
You know, those things that keep our industrial plants humming along in our homes at a comfy temperature.
That's right. They're everywhere.
They really are. But we often don't even realize how complex they are.
Yeah, they do their job so well, kind of behind the scenes that we often take them for granted.
Absolutely. So we've gathered a whole bunch of research and case studies to really get into the nitty-gritty of how these systems work, and even more importantly, what makes them perform well or not so well.
Yeah, and this isn't just for the engineers out there.
Yeah.
Anyone who deals with processes, even in their everyday life, can benefit from understanding a bit more about how these systems work.
That's a great point. So let's start with the basics. What do we actually mean when we talk about control performance?
Well, think of it this way. Imagine you're trying to keep a room at a specific temperature, right? Control performance is all about how well that system, in this case your thermostat, can maintain that desired temperature even when things are changing around it, like the weather outside.
So it's like a constant battle against disturbances. So how do these control systems manage to stay on target?
It's all about feedback control. These systems are constantly measuring the process variable, that thing we're trying to control, like the room temperature, and then adjusting their actions based on how far off it is from the target we set.
So it's not just about turning the heat on or off. It's about making these constant little adjustments based on the information the system is getting back.
Exactly. It's like when you're driving a car, you're constantly making tiny adjustments to the steering wheel to keep the car going in the right direction.
Makes sense. Now, our source material talks about two main methods for figuring out how well this whole control thing is working: frequency response and dynamic simulation.
Right, those are the two big ones.
Can we break those down a bit? They sound kind of technical.
Of course. So frequency response is basically looking at how well a system handles changes that happen at different speeds.
Okay.
Like if you turn the volume knob on your stereo really slowly versus really quickly, a good system should be able to respond smoothly in both cases.
So it's not just about responding, it's about responding appropriately to how fast things are changing.
Exactly. And then we have dynamic simulation, which is like creating a virtual model of the entire system.
Okay, so it's like a test run in the digital world.
Exactly. We can use simulations to run all sorts of experiments and see how the system behaves under different conditions without actually having to risk anything in the real world.
That's pretty cool. Now, one thing that keeps popping up in our research is this idea of dead time and how it can really mess with control performance.
Mm.
What exactly is dead time?
Dead time is simply the delay between making a change in the system and actually seeing the effect of that change.
Hmm? Okay.
It's like, waiting for your toast to pop up after you push the lever down.
Uh-huh. Okay. I get that. But how does toast relate to, say, an industrial process?
Well, imagine you're trying to control the temperature in a giant reactor. If
Yeah.
there's a big delay between adjusting the heat and seeing the temperature in the reactor actually change, it becomes really hard to keep things stable.
Right, because the system is always playing catch up.
Exactly. And that can lead to all sorts of problems like overshooting the target temperature, undershooting it, or even potentially dangerous situations.
Yikes. So it sounds like the nature of the process itself plays a big role in how well a control system can do its job.
Absolutely. And that leads us to this concept of self-regulation, which is basically how inherently stable a process is on its own.
Self-regulation, so is it like the process is doing yoga to stay centered or something?
Haha, not quite, but I like the image. Think of it this way. Some processes are just naturally more resistant to change.
Okay.
Like a huge tank of water, it takes a lot of heat to change its temperature significantly. That's a process with a high degree of self-regulation.
So it's like it has this built-in buffer against disturbances.
Exactly, and that means that some processes are just inherently easier to control than others.
So it's not always the control system's fault if things are going haywire.
Right, and our source actually gives a great example of this with a stirred tank heat exchanger. They found that by modifying the design to boost its self-regulation in this case, by making the heat transfer area bigger, they were able to get much better control over the temperature.
So you can actually engineer a process to be more controllable right from the start.
Precisely. But of course, there are always trade-offs.
Right. There's no such thing as a free lunch.
Exactly. Sometimes making a system more resistant to one type of disturbance might actually make it more sensitive to others. So it's all about finding that balance.
Okay, so we've got this interplay between the control system and the process itself. But what about the controller itself?
Yeah.
You know, all those settings that determine how aggressively it responds to changes. That seems pretty important too, right?
Oh, absolutely. Those are the controller's tuning parameters, and they're crucial. It's like adjusting the sensitivity of a smoke detector.
Right.
If it's too sensitive, it'll go off at every little puff of smoke. But if it's not sensitive enough, you might miss a real fire.
And how does the accuracy of the model of the process fit into all of this? If the controller is making decisions based on bad information, that can't be good, can it?
You're exactly right. Having an accurate model of the process is super important for good control. It's like having a reliable map when you're navigating. If your map is wrong, you're probably going to get lost.
I like that analogy. So it sounds like good control boils down to a few key things: a deep understanding of the process itself, careful tuning of the controller, and a good, accurate model to work with.
You got it. And the good news is, our source suggests that even approximate models can be enough to get pretty decent control in many cases.
That's reassuring.
Eh,
So we've talked about the importance of understanding how the process behaves, the role of dead time, the concept of self-regulation, and how things like controller tuning and model accuracy all come into play. It's a lot to digest.
it is, but we're just getting started. There's still so much more to explore. How about we dive into this manipulated variable thing and how it affects the overall performance?
Yeah, let's do that. So what's the deal with this manipulated variable?
Well, it's basically the tool that the control system uses to try to nudge the process in the right direction. In our thermostat example, it would be like the amount of heat being pumped into the room.
So it's the thing that the system can directly control.
Exactly. And by controlling that, it indirectly influences the process variable, which is the thing we're actually trying to keep stable.
Okay, makes sense.
Hmm.
But I imagine there's got to be some kind of balancing act here, right?
Oh, yeah, absolutely. There's often this trade-off between keeping the process variable really tightly controlled and making sure the manipulated variable stays within reasonable limits.
So you don't want it to go completely haywire.
Right. It's like steering a car. You want to stay on the road, but you don't want to be jerking the steering wheel back and forth like crazy.
Uh-huh. Yeah, that wouldn't be a very smooth ride.
Hmm.
So how do we find that sweet spot, between being responsive and keeping things nice and stable?
That's where analyzing the system's frequency response comes in. Our source is a really good example of how changing the controller gain, which is like this sensitivity setting, impacts both the process variable and the manipulated variable.
Okay.
And by finding just the right setting, we can get good control without making the system work too hard.
Makes sense. Now, we've been talking a lot about the process itself and the controller, but what about the other parts of the system, like the sensors and those final control elements? They're kind of like the eyes and ears of the whole thing, right?
You got it. We can't forget about those guys. They might seem like small details, but how quickly and accurately they respond can have a big impact on how well the whole system works.
Yeah, I guess even if the control is making the right decisions, if the sensors are slow or if the final control element, like a valve, takes forever to react, that's going to mess things up.
Exactly. It's like having a delay in communication. The brain might be sending the right signals, but if the arms and legs are slow to respond, the whole body's going to suffer.
Right. Our source actually compared the control performance with and without, considering these little delays, and the difference was pretty huge.
Yeah, it's really important to take those things into account. And speaking of things that can affect performance nowadays, a lot of control systems are digital, right?
Right.
Instead of constantly monitoring and adjusting, they're making decisions at specific time intervals. So that adds another layer of complexity to the whole thing.
So does that mean that faster updates are always better?
Well, not necessarily. If the updates are too frequent, it can actually put a lot of strain on the system without any real benefit. The key is to make sure the updates are happening often enough to keep up with the changes in the process, but not so often that they're causing problems.
So it's all about finding that balance again.
Exactly. Now, when it comes to actually designing the controller itself, our source talks about these different control modes: proportional, integral, and derivative. And it seems like the integral mode is pretty much essential in most cases.
Yeah, that one seems to be the workhorse.
Right, because it's what eliminates that steady state offset, meaning it makes sure that the process variable eventually settles down exactly where we want it at the set point.
Okay, but what about the other two modes, the proportional and derivative ones? When do those come in handy?
Well, the proportional mode adds this immediate response to deviations. The bigger the deviation, the stronger the correction. And then the derivative mode is a bit more sophisticated. It looks at how fast the error is changing and tries to anticipate what's going to happen in the future.
So it's like having a team of experts. The proportional guy is all about the here and now, the integral gal is focused on long-term accuracy, and the derivative whiz is trying to predict the future.
Uh-huh. That's a great way to put it. And just like with any team, the best combination of skills depends on the specific job they need to do.
Right. And speaking of choosing the right tool for the job, our source also talks about the importance of picking the right manipulated variable. It seems like it's not always obvious which variable to use to control the process.
Absolutely. Sometimes there are multiple options, and choosing wisely can make a big difference.
So how do you decide? What are the things you should be thinking about?
Well, our source gives some good guidelines. You got to look at how strong the connection is between the manipulated variable and the controlled variable, how fast the response is, and how well that particular variable can handle the biggest disturbances we expect to see.
So it's like choosing the right lever to pull.
Yeah.
You want one that's going to have a direct impact, that's going to react quickly, and that can handle the toughest challenges.
Exactly. They actually compared two different manipulated variables for controlling the concentration in a reactor, and the results show how the right choice can make a huge difference.
Wow, that's pretty cool. Now, one last thing that really stuck with me is this idea of designing processes with control performance in mind. It seems so much smarter than trying to fix problems after the fact.
Oh, absolutely. It's like being proactive instead of reactive.
Yeah. So can you give us an example of how that might actually work?
Sure. Our source brings back the stirred tank heat exchanger. By making the heat transfer area bigger and carefully choosing the coolant temperature, they were able to make the process much less sensitive to those fluctuations in the feed temperature.
So they basically built in this resilience to make the control system's job easier.
Exactly. It's like designing a house with really good insulation. You don't need to use as much heating or cooling to keep the temperature comfortable.
I love that analogy. It makes so much sense. Okay, so we've covered a lot of ground here. From the behavior of this manipulated variable and those sensor and element dynamics to the whole world of digital control, and even the importance of picking the right control modes and the right variables to manipulate. We even touched on this idea of designing for controllability from the very beginning.
Phew. Yeah, it's been quite a journey. But believe it or not, we've only just scratched the surface of this whole control systems world.
It really does feel like there's a whole universe of knowledge hidden within these control loops.
There is. And luckily, our source actually provides this really handy table that summarizes all the key factors that affect how well a single-loop PID controller performs. It's a great reference for anyone who's actually working with these systems day to day.
That sounds super helpful. But even with all this information, it seems like there are going to be situations where a simple PID controller just isn't enough to get the job done.
You're right. There are definitely limits to what a single-loop controller can handle, especially when you're dealing with really complex or nonlinear processes.
So what happens then? What are the options?
That's where things get even more exciting. There's a whole world of advanced control techniques out there. These techniques use multiple measurements, predictive models, and even artificial intelligence to get even tighter control and really optimize performance.
Wow, that sounds like a whole other deep dive waiting to happen.
Yeah.
But for now, I think we've given our listeners a pretty solid foundation in the fundamentals of control performance and all the different factors that can affect it. It really is amazing how much goes into making these systems work so well.
It is. And I think one of the biggest takeaways for me is that it's not just about the controller itself. It's about understanding that whole process and how all the different parts interact and influence what the controller can actually do.
Yeah, it's like a team effort, right?
Exactly.
And we need to make smart choices, not just about how we tune the controller, but about how we design the process itself to get the best possible performance.
Absolutely. And we always got to remember those disturbances are out there lurking, just waiting to mess things up. So building in that resilience from the get-go is super important.
That's so true. It makes me think about all the ways that these control systems impact our everyday lives.
Yeah.
We've been talking a lot about industrial processes, but these same principles apply everywhere, right?
Oh, yeah, for sure. I mean, think about your car's cruise control, the autopilot system on a plane, or even the way your own body regulates its temperature.
Wow, yeah.
Feedback control is working all around us, constantly trying to keep things stable and predictable.
It's kind of mind-blowing when you stop and think about it. So, to wrap things up, what's one key insight you hope our listeners will walk away with from this deep dive?
I think the most important thing is to remember that control systems aren't just these magical black boxes. They're complex systems with their own logic and behavior. And by taking the time to understand how they work, we can design, operate, and troubleshoot them way more effectively.
That's a great point. It's not about memorizing a bunch of formulas. It's about really understanding the underlying principles.
Right.
and then using that knowledge to solve real-world problems.
Exactly. And that understanding can be applied in so many different areas, whether you're an engineer, a scientist, or just someone who's curious about how the world works.
Well said. Thanks again for taking us on this journey through the world of control systems. It's been fascinating.
My pleasure. And to all our listeners out there, the next time you come across a control system, whether it's your thermostat or something way more complex, take a minute to appreciate all that intricate work that's happening behind the scenes.
Great advice. Thanks for joining us on this deep dive, everyone, and we'll catch you next time.